Hi everyone, I'm Abdurrahman, and in this video I'll be showing you how we can analyze a four-bar linkage using MATLAB to figure out its motion and its angles, velocities, and accelerations of specific points of interest. Thus, by the end of the video, we'll be able to create an animation similar to what we are seeing at the moment. So, to start with, first of all, we need to analyze the four-bar linkage to get a closed form equations that we can use in MATLAB. Then we'll see how we can write the MATLAB code. After that, we'll be discussing some theory regarding the four-bar linkage to see or to figure out what is expected to be seen from the MATLAB code. And then with that, we could see if we have anything in the MATLAB code that needs fixing or not, since the code will always give us an output regardless if it's correct or not. All of that depends on whether what we input or what we code is correct or not. So to start with the analysis, we have this four-bar linkage. So the terminology used is that we'll start with the ground link as link number one, then we have 2, 3, and 4, and we have the lengths of the links, as we can see, being A, B, C, D, and the angles are defined as follows. Also, it's important to see the direction of the vector, where link 2 goes from the origin, the left anchor, to its end. Link 3 goes again from the end, starts from the end of link 2 and goes to the right. Link 1 starts again from the left anchor, which I'll be using as the origin, and goes to the right. And link 4 starts from the anchor to the right and goes to its end. So to analyze this and get the unknown angles, first of all, we need to know what is known and what is unknown. We know the length of the links, since those are design parameters, and since we will input the motion via link 2, theta 2 is known. Thus, what is unknown is theta 3, theta 4. And theta 1 is known since it will be 0 in this case. So with this known, what we can do is that we could write a vector loop equation. So what this says is that we have vector of link 2 R2. If we add it to vector 3 R3, subtract R4 since it's in the opposite direction, and then go back in the opposite direction of R1, what we will have is that all of those should add up to 0 since we came back to where we started. And this is what we see. The vector of R of link 2 R2 plus R3 minus R4 minus R1 should be equal to 0. Then what we could do is that we could write each vector in its complex polar form, where we have its magnitude multiplied by a complex exponential, where we have e to the power of j, which is the imaginary number square root of minus 1, times the angle of that link. With this, we could use Euler's identity to expand it using cosines and sines to have the following. At the same time, we could simplify the last one, since we know that theta 1 is equal to 0, we will have e to the power of 0, which is 1, and thus we'll be left with only d. And so from here we can see that we know everything a, b, c, d, and theta 2, except theta 3 and theta 4, which are two unknowns. At the beginning, it might seem that this is one equation, but since this is a complex equation that has both real and imaginary parts, the only way for it to be equal to 0 is that for both the real and imaginary parts to be equal to 0. And thus, by separating those parts, we'll be having two equations. One that is for the real part, which in this case will be the x component, and the other one will be the imaginary part, which will signify the y component. Thus, we have two equations and two unknowns. Thus, solving this after a lot of algebra will give us the following solution. For theta 4, we will have this equation. For theta 3, we will have this equation, where the constants are defined as follow from A to F, and each of those have other constants from K1 to K5, which are defined as follows. As we can see, everything is defined using the length of the links, which is known, as well as theta 2, which is also known. Something important to note out is that we have here a plus minus, and thus we have two solutions for each angle. Those signify two different, you could say, configurations of the linkage. One is open and one is crossed, and both of them are physically applicable, so that we could use any of those depending on how we assemble the mechanism at the beginning. However, we should be consistent. If we use here the minus sign, which is in this case the open configuration, we should use it in both angles, theta 3 and theta 4. And if we use the plus, which is the cross, we should use it again in both. With this, we have a closed form equation for both angles for the lengths of interest. Then we would need to get the velocity and acceleration. For that, we will do exactly the same thing. We will reach the same equation for the vector loop equation, but to get the velocity and acceleration, we will need to differentiate this equation once to get the angular velocities and twice to get the angular accelerations. So differentiating this once, we will get the following, where we can say since the length of the link is constant, this will be left alone, and then differentiating this with respect to time will have itself times the derivative of its exponent. Since j is also a constant, it would stay outside, and the derivative of theta 2 with respect to time is theta 2 dot, or omega 2, which is the angular velocity of that link. Similar thing applies for all the other links, and it should be noted that for the last one, since theta 1 is equal to 0, we will have here only d. D is the length of the first linkage, which is the ground, and since it's not changing, it will be equal to 0. That's why we are not seeing it here. Differentiating this again with respect to time, we will get a similar thing for the angular accelerations. Here we can see that everything is known, alpha, A, B, C, as well as theta 2, theta 3, and theta 4, since we got the equations for those two angles beforehand. Omega 2 is also known since, again, it is the input. We know how fast we are moving our input link, and thus the only unknowns are omega 3 and omega 4. Same thing applies for the angular accelerations equations, where we have A, B, C all known, theta 2, theta 3, and theta 4 all known, omega 2, omega 3, and omega 4 known from the previous equation, from the velocity analysis, and alpha 2 again is known since it is our input, leaving us with only alpha 3 and alpha 4 to figure out. Again, since this is equal to 0, both the real and imaginary part should be equal to 0. Thus, a similar process to the position analysis will be used. Expand this using cosines and sines, separate the real and imaginary part, and solve the two equations for the two unknowns, leaving us with those closed form equations for omega 3 and omega 4, as well as alpha 3 and alpha 4 with those definitions for the constants. From here, we can go to the MATLAB code to see how it works or how we could code it. To start with, what we need to do is we need to figure out how to start our code. Always we start with what we know. So first of all, clear CLC and close all figures. And from there, we will have input what we know. We know the length of the links, which will be the input. In the MATLAB code, as we saw before in the animation at the beginning of the video, we have here an extra link with a point P at the top. And so for that, we know its length and the angle it makes with theta 3, since we can think of it as a ternary link and the shape of that link is known. So we know its length and the angle it makes. And then we will have also other inputs, which are theta 2 and theta 1. For now, we will use only one value for theta 2, but later we will change this to be a vector so that we will have a full animation for all the different values of theta 2. Theta 1 is known as 0, since in this case it's horizontal. And as you can see, we should always in this case convert all the angles to radians, so that in the next analysis of velocity and acceleration, we will not have issues, because working with degrees will not always give us what we want. So it would be better to work with radians per second or radians in terms of the angles. Then we also know the angular velocities and accelerations. And finally here, those are empty vectors that will be used later to store the x and y position of point B and point P. From here, we can now simply input all the equations that we know for the thetas and angular velocities and accelerations. So here we have the equations for k's, equations for the A to F, and then the equations for theta 3 and theta 4. Here we can see we are using the open configuration. Then we could again input the equations for omega 3, omega 4, the variables for the angular accelerations, and the equations for those two. From there, we can now find the vectors describing the links in the Fourbar linkage. We have R1, which in this case is simply its length, R1 times the complex exponential, e to the power of its angle times j. Same thing for all links. And here we can see that for link 5, its magnitude is its own length, but its angle, we can see that it is theta 3 plus alpha, since this is constant, since it's a solid body. From here, what we can go now is that we can now plot what we have, since we have everything ready. We can start a figure, clear anything in the figure. This will be used later when we create an animation, where what we will do is that plot the four-bar linkage for one theta 2, clear the figure, and plot it for the next theta 2. And as this moves, we will have different frames, and those will create the animation or motion for the four-bar linkage. This simply sets the font size, and those are used so that we could plot all the different links, and this to show the grid. Here we are using axis equals so that the x and y axis will have similar scales so that we can have a better vision or understanding of how the links works, because if this is not used, the scales might be different and thus it might be misleading. To plot the links, what we need to do is simply plot the two endpoints of the vector. So for instance, for link 1, we know that it starts at 0, 0. So here, this is the x and this is y. We start at 0, 0, and then we go to the real part, which is the x component, and the imaginary part will be the y component. So the x will go from 0 to the real part, and y will go from 0 to the imaginary part. Same thing for link 2, and for all the other links. For instance, for link 3, in this case, we don't start at the origin, but we start at the end of link 2. So we start at a real and imaginary of R2, and then we end at the sum of both of them. So we start from the origin, add R2, R3, and this is where is the end of R3 relative to the global coordinate system. We do the same thing for all the other links, and by running this, we can see here the linkage, the four-bar linkage as shown here. However, as you can see, it's on the edge and it does not really have enough space. And if this will be rotating, then it will go out of the frame. So what we could do is that we could set the axis in this case to be as follow, with space x0, x1, y0, and y1, and we could simply set it in here. I just wrote those to make sure that during the animation, the links or the four-bar linkage will be in the axis, in the frame for all theta 2s as this link rotates throughout. And so with this, we have the basic four-bar linkage. Now what we'd like to have is that we'd like to have graphs that show the velocity and acceleration as well as the angle of link 3 and link 4. For that, we could simply start by inputting this subplot so that our figure will be divided into different tiles so that we can put different graphs at the same figure. So here we can see that we have 3 rows, 2 columns, and for this one, the first one that shows the linkage, it will use tile 1, 3, and 5. And so the tiles are counted in MATLAB from left as 1, 2, 3, 4, 5, 6. So it will take the left half of the figure. With that ready, we could now simply plot the acceleration and the velocity. So here we have, as well as the angle. So we have here the second tile, which is 1 to the top right one. We will have here the angles. And as we can see here, in the last case, only we change from radians to degrees so that we could see the results in degrees. But all the computation is done using the radians. Again, similar to what we did, setting the font size, adding the grid, holding everything so that we could plot different curves in the same figure without deleting the first ones. And so with this, we have the following result. We have on the left side the four-bar linkage, and on the right side, we have theta 3, theta 4 for the given angle, as well as omega 3, omega 4, and alpha 3 and alpha 4. We can now, for instance, change this to any angle we would like, run it, and we will have it for different angles. However, now we would like to automate this. And so for that, what we could do is that we could go from here and go length space from 0 until theta 2 max with whatever number of points. For now, let's start with 30 until everything is fine, and then we could increase it, since this will essentially be the number of frames in our animation. So with that, what we could do is that we could simply wrap everything we had here in the plotting and everything that uses theta 2 in a for loop. So we could simply go for I equals 1 until the length of theta 2, and then we could end it after everything is done. Now what we need to do is that we need to take out the figure outside, otherwise in this case we'll have 30 figures, one for every theta 2, which is something we would not like to have. And the last thing is to change every theta 2 here to theta 2i, since now our theta 2 is a vector, and so we want only every ith theta 2. Doing that, we will get we could get the following. Taking this, we'll have the following. The only difference that I did is that I added here, I set the figure to a variable so that we could control it. For instance, here setting it to be maximized. Here I'm using the pause, which will stop the code running at this point for 5 seconds, so that I could bring the figure from the other screen to this one so that we could see the animation as it goes. And here nothing changed. I simply changed all the theta so that there's an I of it, so that will take theta 2 of the ith term or element in the vector. And recalculating everything, plotting everything until everything is done. So running this script, we see here, so nothing is done since we are paused for 5 seconds, and then everything starts. It seems that there's an error where we have the axis is undefined, the axis limits. So we could simply redefine those. So with this, here we go. We have the final results. However, we didn't see how the linkage was moving as it went, but as you can see from the graphs, we can see that this is like the 30 points we want. It goes from 0 up to 360 for theta 2. And we have here the path of the points of interest. However, for us to be able to see what is happening, what we need to do is that we need to add here a pause of something like a 0.1 seconds, so that as everything is drawn, the code stops, so we could see the frame, and then it goes to the next frame. So running it again, you can see here the first 5 seconds, and then as you can see, it plots one, waits for 0.1 seconds, plots the next one, and it goes so on until we reach the end. However, as you can see, it's a bit slow since there is a lot of calculations that should be performed. And as we increase the number of frames from 30 to, for instance, 360, so we'll plot it for every degree, it would be better if you could save it to a video file, MP4 file, and then watch it later, so that everything will be ready without the need to calculate every frame and every angle for every configuration or theta 2 given. So for that, what we could do is that we could simply add a video writer object. Here we could set the file name and its format. This format will simply give us an MP4. And then we could set the frame rate, in this case 60 FPS. We could open our video writer, and then here a pause of like a quarter of a second, just so that everything is fine. Because if without this, it might cause some issues. And from there, everything and the rest is the same without any change. The only thing is at the end, what we'll have is that we'll have the frame using the get frame f, where f is as defined before, it is the figure. So after everything is drawn in the figure, we save that figure into a variable called frame. And then we write it to the video writer object. In this case, we don't need to put this pause since it will simply slow it, or we could add it if we would like to see it in real time as the video is being saved. And then after that, we need to close the video writer so that the file or the animation is saved without any problems. Otherwise, without closing it, even if the script finishes, we would still have an issues. For instance, if you try opening the file, it will give you, for instance, stuff like the file is corrupted or it's not supported. With this, we have everything needed. We could run it, and here we can see how the animation would go. As you can see, without the pause, we are still seeing it because the action of simply saving it to a file takes a lot of time, and thus it in itself acts somehow as a pause function. And so with this, we have everything ready. We have the paths for the points of interest. We can see the animation, the points or the angles, angular velocities and angular accelerations are fine. So from here, we could now increase this to a higher number and see how it works. However, just to show it, this is the file that we showed, and it will save it in the same destination where the script is found. So running the file, as you can see, this is what we had. Since we had only 30 frames and the speed was 60 frames per second, our video length is only half a second. But it shows the similar results without any slow motion similar to how it was when it was running live on the script. So changing this to 360, we could again rerun it, and it will do essentially the same thing but for more number of points. So here theta 2 will change for every degree, and as you can see here, there are more points that are given in the plot. Stopping it, we can see then the theory regarding those. So going back here, the first thing that we'd like to check, and that is important for a four-bar linkage, is its Grashof condition. So given S is being the shortest length and L being the longest length, with P and Q being the two other lengths, if S plus L is less than P plus Q, then it is a Grashof, which means that at least one of the lengths is able to have a full rotation. If it's not, if S plus L is greater than P plus Q, then it's non-Grashof, and thus there is no link could perform a full rotation, and thus it will give us triple rocker for bar linkage. And finally, if both of them are equal, this is a special case of Grashof condition, which is at the limit of both of those. One link could rotate fully, but there will be inflection or changing points during the motion of the linkage. The next thing, since in our case we'll be working only with Grashof uh, links or mechanisms, we could use Barker's classification for this case to expect or to predict what would happen or what type of motion we'll be seeing. So in the cases given to us, we could simply check, for instance, in here, which one is the shortest link, and from how we were defining it in the beginning, with this being link 1, 2, 3, and 4, using those, we could know which type of motion is expected. If the shortest length is grounded, then we'll have a double crank. If it's the input, we'll have a crank rocker, and so on. And so our cases are as follow. This is case 1, where we have the ground link being 4, second input link 2, 4, and so on. So with this, what I will be doing now is that I will show here the final code, which is essentially similar to what we had beforehand, but I simply added comments to make it clearer, and I changed, for instance, here the subplot to a different one so that I have a better control over where the different tiles or graphs are found. So running this, it will give us similar stuff, but as you can see, like the formatting is different so that it is somehow more organized. And by testing those of two results, we can get for case one this animation, which since here we can see that the shortest link is the input link, which is 2. We can see that it is as expected. Since S is the input, it's a crank rocker. So the input is rotating fully, so it's an a crank. And the output one here, the light blue link is rocking between two extreme points. For case 2, similar thing is seen. So if we open the second case, we can see similar stuff. Here we have the shortest link being the input, and thus we will have a double crank motion. As you can see, the input is giving a full rotation as well as the output, and here we can see how both of them are giving a full rotation. At the same time, you can see how the angular velocity and angular acceleration are developing as theta 2 is increasing. With this, you can have here a look on the code, and with this, the video is done. Thank you for listening, and have a nice day.